Well, outline my lecture. First, view equation of fluid saturated soils and solution of dynamic elastoplast. In this one-point integration of core nodes by parametric element with hourglass control. Non-linear solution might avoid accumulation of error. And implicit, explicit dynamic relaxation method of static problem. Dynamic and static, both problem. Second, material model for plastic behavior of soil. A elastoplastic constitutive model of cohesive soil, such as clay, and generally data mapping method apply, and viscoplasticity included, and elastoplastic constitutive model of granular material, such as sand and rock-fill material. Third, shaking table test of embankment dam and dynamic analysis. Dynamic analysis of model dam by elastoplastic constitutive model was carried out, and then comparison of 2 and 3 dimensional dynamic analysis was made. Fourth, elastoplastic dynamic analysis of existing real dam. Existing dam analysis by applying elastoplastic. The acceleration and response ratio, earthquake or response ratio, the crest acceleration or base acceleration. This the Biot equation. Biot developed a theory of viscous fluid saturated soil. Dynamic analysis of saturated soil is usually carried out by a numerical method, binary method, involving discretization of both space and temporal domain. In this equation, MES, a ramped mass matrix, bulk of solid particle. MEF, a ramped mass matrix, and we are using ramped mass. So MC equal delta. H in this H in dissipation matrix. Now you W vector of displacement of solid particle, W vector of displacement of fluid with respect to solid particle. And the standard load vector of bulk solids. And G is the load vector of normally equal to. So explicit dynamic relaxation method in this equation, P is given by this strain displacement matrix and sigma. So, internal force. And MD A is acceleration. The solution scheme of central difference method is effective. Replacing damping by C equals alpha MD. And in this equation, R, the damping ratio, which is the most critical value to be determined. So each small time increment, alpha is always changing. So delta T is the time of increment. Explicit method is not suited for stiff and thin structure, such as sheet of pile, because of the severe coolant condition. So we shall be solving a differential equation which can be written as CTV KTQ equal dynamic method or dynamic regulation method with an implicit explicit type in effect solve structure interaction problem. So this equation Q displacement V the velocity and A is acceleration vector. And gamma beta constant. And this formulation is based on numerical method. In case of implicit element, 4-point integration is applied, such as sheet pile. And explicit element, 1-point integration is applied. This one is diagonal. And this equation solved. Displacement is simultaneous solved from the explicit and the implicit effective stiffness matrix using the skyline solvent. And implicit explicit method, skyline solvent is essentially important. This skyline method is developed at the back. So for residual force is evaluated by the equation and the displacement, velocity, acceleration obtained like that. Applying this procedure, very big three-dimensional problem, for example, 1 million, can be solved. Second, material model of plastic behavior of soils. Elastic constitute model 1 of cohesive soil. So plastic constitute of cohesive soil at 2 yield surface. So this shows yield surface of plastic model cohesive soil. This F1 failure line. F2 work hard chart and just critical state line. So molecular type failure surface, the elliptical chart model with a strain hazard in consolidation process. Both are connected on the critical state rock, and the numerical instability is most likely to occur on the critical line. So, to use the surface, we apply iterative and converge to this singular point, which is very important point. So, yield function. In case of critical state, this one, K of that. This one is molecular failure line. And alpha function of internal friction. In this equation, G theta L, in case of molecular failure line, include This one elliptical cap also G theta include. So pi plane G theta L takes this function and the shape just pyramid line. So this one is a Dora coupler. Anyway, G theta L Rhodia, and this is the third invariant of Biot strength. Rather complicated one. The general return mapping, a change in stress can cause an associated change in the elastic strain. And this process, the return mapping process, the change in stress, sigma A, sigma B, sigma A elastically predicted stress, and sigma B stress reacts on the suitably updated side. These are free. The plastic strain change is balanced by an equal and opposite change in the elastic strain. This is the basic point of return mapping. And the epsilon ij, total strain increment, equal elastic strain increment. When S equal 1, plastic strain increment. But introducing S is the region. In this equation, Fe is the area of the element, finite element. Fb is the area of single shear band in each element. This S is ratio, area ratio. This was introduced. So I say newly defined additive decomposition. Plastic strain increment, the epsilon P equal lambda by lambda single pi is plastic potential. Lambda is unknown function. And the suitably relaxed stress sigma B is given by this equation, including area ratios. And this put into the function F. And applying Taylor expansion, we can determine lambda. The model can incorporate characteristic lengths of shear band in the material modeling based on physical experimental observation of strain localization into a finite size shear band. This shear band having a sequence in proportional to the mean particle size around 50. This shows this called plasticity model. We employ general three-component model. So, elastoplastic or viscosity force. The rate-dependent constitutive equation, dual-Arion model will be used. This model is applicable to singular point. In geomaterial, singular point is very important. So So Pesina type model are in general not meaning when the elastic domain is defined by several surveys. For similar point, Pesina type is not good. So one-dimensional viscoplastic model, a new isotac model, I provide that as well. Develop this model, depend on the great deal of experimental results. The stress, the unique function of instantaneous irreversible strength and its rate. G, the viscosity function, and the equivalent grid parameter necessary for the volume, eta is given by this equation. This model, another model was developed by Tatoka and their team. Anyway, this equation is essentially one dimension based on experimental result. We need to extend this one-dimensional model to three-dimensional model by using this tensor equation. So for next, elastoplastic constitutive model of granular material. Yield function is given by this molecular type. And plastic potential function is Dirac-Kaplan type. Both, if we use same form, then that problem occur. So plastic potential function, not including G theta L, Rojan not included. First, I'd like to talk about the simple strength softening constitutive of granular material. Sometimes it is right. Frictional softening is given by this simple equation. Cohesion is also given by this. Dilatancy is reduced by this equation. Of course, we need equation cut by the plastic parameter. ACD are constant. Okay. For elastoplastic constitutive model of granular material too. So hardening regime, we use this function. Developed more mainly complete field. But in practical application, sometimes this hardening regime is replaced by elastic property for practical problem. And this is softening regime or hardening regime. Softening a function exponential. Of course, cut by plastic parameter. Where M epsilon M, epsilon R, but anyway, softening regime determination of this bar epsilon R is very difficult, not easy, because we investigate stress strain relation within shear band. And in this model, dilatancy R is given by stress dilatancy relation. This stress dilatancy relation was developed low. This function a little bit different from law, and by R, right? Residual one is a little change to fit the real material. So for granular material number 3, kinematic hardware model. This is the primary use. Of course, in case of molecular model, this takes pyramid shape. So let's reverse from primary yield surface. Secondary yield surface generally. And when stress reverse, this secondary surface disappear, new yield surface generally. Just show calibrate stress strain relation to reaction test. First, primary yield surface, and then unloading. Plasticity is included in unloading case, and reloading, and then primary yield. Anyway, this kinematic hardening model within bounding surface, these parameters are rather difficult. So it is not easy to apply to practical problem. This shows a relation between deviator stress and axial strain. Deviator stress, axial strain in triaxial consolidated terrain to test by elastoplastic model 1. This one, sorry. Just show one-dimensional consolidation. In this computation, finite element mesh with 10 elements, depth of the layer, 10 meters. It shows the settlement and time factor. And in case of elastic material, just same certain consolidation. And in this one is elastoplastic. And this one is viscoplastic. Isotac and this. Just show finite element analysis of direct shear box test simulation. So the gap between the upper and the lower box are 0.05 centimeter. Upper box is upper box, which move horizontally and vertically. Material of box, the linear elastic. This show relationship between shear stress and horizontal displacement. This one can consolidated drain condition. This one experimental result, CD condition. But anyway, consolidated test in clay is not easy. Just show computed relationship between shear stress and displacement for sand material. Elastoplastic analysis and isotac viscoplastic analysis as shown. And this one, direct airbag test, fully drained condition. And this one, I stack model with very slow. And this shows excavation problems in clay. Modeling of structure in test pit. Marinsky Theater in St. Petersburg. Five model. This. And the struts, part of the strut. These are incrementally installed. Soil property, soil assumed to be all cohesive. There because of undrained condition and cohesion of soils are determined by design classification. The calculated displayed. These are measured. Next, I will talk about the plane strain test and finite elemental analysis with various shear band sequence, stress ratio and shear strain of plane strain compression test by finite elemental analysis using only one element. So this is granular material. So SD, the shear band width. This one without shear band is elemental. All which is elemental within shear band. So anyway, just without the shear band. And this one, 1.2 centimeter. This one, 0.6. And this one, 0.3, 0.15. The experiment result from a peak to a residual state is approximately identical to computed relation with shear band thickness 0.3 centimeter. We normally use 15 times the mean diameter of granular material. So that part, shaking table test and embankment dam and dynamic analysis. This shows embankment model and the location of acceleration. We are using Toyota Sun, very loose, and this shows the finite element image. These are observed acceleration at the base, checking data, and the crest of the dam. Input horizontal acceleration observed at the base of data. The acceleration simulating eccentric pathway can be used. And this one observed acceleration at crest of the dam. After experiment, displayed of GSR 12 centimeters. Just show computed acceleration. This is a computed acceleration and computed settlement at the center of thermocracy. Without the 5 centimeters. Similar result are obtained. Just show three-dimensional finite element analysis whether the checking table. Just show computed horizontal acceleration and settlement correct. Whether the computed horizontal acceleration in 3 dimensions. A little bit higher acceleration. And just show computed settlement at the crest of model down. A little bit. This is a graduate of the fourth part. Elastoplastic dynamic analysis of existing. They are done. Just show landslide by Hokkaido earthquake. Magnitude 6.6. And this earthquake struck southern Hokkaido 2018. The earthquake caused many roads to become impassable, and many have buried. Over 40 people are died. Around this area, every hill or mountain area, slope, slide down. Mizuho, this lab located near the epicenter of this earthquake and strongly shaken. Record peak acceleration at the base of Mizuho Dam in upstream and downstream direction was 491. Maximum settlement of pressure was from 10 to 12 centimeters. And cracks attained 2 meters depth, but observed around the cross. This showed cross section of Mizuho Dam, 7 meters at the crest and base. This way, the cordon number 2, semi-permeable, and the filter zone and the refractor. Without acceleration at the Mizuho Dam, this one at the base. Peak acceleration 937 GAR at the record at crest. We analyze this problem using 1-point integration in the linear isoplanar area problem. Anti-hourglass scheme was used to prevent any probable hourglass movement. Settlement of crest around 12 centimeters. And major crack. This downstream through. Material parameters for dynamic analysis obtained by this table. strength of core material is obtained isotorically constituted and undrained reaction. Shear band thickness is assumed to be 0.5 centimeter. Semi-permeable dome are considered to be undrained, and the shear band thickness is assumed to be 3.0 centimeter. In this table, this bracket shows case 2. Here the figure shows computed acceleration at crest of middle down, computed acceleration. And this one, computed displacement. This one is at the crest. Almost similar result. This shows computed maximum shear strain distribution. Maximum shear strain. And around this severe crack, we occur. So cross section of another near middle down. And this dam is higher than middle down. Some core and number 2. Semi-permeable zone, mainly mudstone. Mudstone is used in the filter and reply. This shows observe acceleration at Admata based on this dam, 300 car, and the crest 1,300 car was observed. This figure shows measure the surface settlement of Admata around 15 centimeters settled at the crest. So this table shows material parameter with dynamic analysis of our time. In this case, almost similar to perfectly plastic analysis was carried out. This figure computed response acceleration and displacement. Observe displacement 15 centimeters. I did a calculate. This one another example. Ogakida dynamic analysis. The Great East Japan earthquake, 2011. This outer rock transition zone core and estimated input acceleration. Very long time acceleration is applied. This figure shows consolidated undrained stress strain relation for the transition zone. This one, simple rule. This one, and the elastic right? Cyclic. So let's apply. For peak load, reduce. So this shows computed result by simple constitutional model. Transition zone will undrain the total so-called total stress analysis is applied. The strength reduction by cyclic behavior in total stress is due to the plasticity or damage, and the cumulative shear strain can be calculated by the elastic strain. And this one is calculated displacement at the crest. Next, dynamic response analysis by applying kinematic hardening elastic plastic model. Effective stress analysis, that is, Biot equation is applied. Constitutive model granular free in use. And this is calculated displacement at the crest. In here, give the measurement 40 centimeter from 40 centimeter to 15 centimeter. Observe. This example is alert data 74.4 centimeter high rock here down and 7.2 magnitude. It just down. The seismic peak acceleration of measured at the base of alpha down and greater than 1.0 G. This shock record acceleration at alpha over 1 G is measured at the base of down. And the crest of the almost half acceleration, but of the just as Lutz and the model test. Finite element of mesh, which is using to analyze the cost mesh. The constitutive model gradual material. This is the calculated acceleration. A little bit greater than octave 1 as a crest. This shows computed settlement at the crest of this down over 20 centimeters. And this is calculated. This computed displacement at the crest of the comparable to observed one. Observed one from 20 to 26 centimeters. Just show acceleration response ratio of another dam and other dam. This acceleration response ratio and the peak acceleration at the base, increasing the base acceleration. This ratio reduces. But in this case, smaller than 1.0, almost half. This shows a section of niche dam. This height is 101 meters. Rock dome, transition dome, grade. Typical Japanese rock dam. And using this input acceleration and increasing maximum acceleration by input weight and the response ratio similar to Karatu going down and over 1,000, 1 T. So response ratio over load 1.0. I would like to talk about summary. Biot developed theory of fluid saturated soil. Applying the theory, plus static and dynamic analysis of cohesive soil and granular material carried out numerical method. Dynamic relaxation method applies to that problem. One-point integration of all nodes isoparallel element with Avogadro's control in the effect. Without avoiding effectively shear locking and dilatancy locking, we cannot obtain reliable solution for soil structure. Constitutive developed for material contain no associated terrain hardening, softening, elasticity. Terrain softening material model of geomaterial is used with the feature of post-peak terrain localization into shear pattern with a specific width. Viscoplastic model of developed and dynamic progressive failure analysis of a small embankment dam using a dry sand on shading type. Shaping tape is carried out. Then, comparison of 2 and 3 dimensional analysis of dry Toyota sand embankment dam also carried out. The computation of existing filter dam are also carried out by total elastoplastic constituted model and effective stress constituted model by taking into account forward data and develop model applicable to the computation of real filter dam. This research was assisted by Hiroshi Mori, Kenji Ogajima, Yoshiki Kimura,